Welcome back to the classroom. We are talking about Earth and space, and today's lesson is titled as How About Mars? So, our lesson intention today is to investigate the type of environment that is on Mars, and what we want to do as a success criteria is to explain whether or not it's possible for Mars to have people living on it and have it cultivated. So, let's begin. So, goes back to one of the questions we posed last lesson, and that is reasons why we might want to move to another planet. One of the main arguments is the continuous pollution, the potential of running out of resources in the near future. We are expected to reach a point where the population of our country or of planet Earth is not being supported enough by the produce of food and all those other resources that we require to survive. So there might be a situation in the future where we might want to move to a nearby planet or move away from our solar system. Then we need to consider some things as to whether or not it's viable for that to happen. Now, obviously, Mars is being one of the things, popular conversation of people bringing up of another place that we could go to potentially in our own solar system. So there have been talks about people, little projects about sending people to Mars and then investigating how they survive and all that. Now, before we get into the nitty gritty of whether or not colonization of Mars is possible, let's actually look at the dangers of going into space first. Okay, so two things that we really need to consider when we're in space. Solar flares. So once we leave our atmosphere, we don't have a protective layer of gas that can block out, or we don't have the magnetic fields to block out really harmful radiation that is being exposed to us. Now that's essentially what our sun does, right? It exerts really highly energetic radiation that is ionizing, so it can have the potential to manipulate DNA and all that. So that's one of the things we need to consider. We do have spacesuits, but obviously it wouldn't be viable to continuously wear spacesuits all the time. And the other thing is the changes to gravitational force. Obviously, when we are out in space, how our bodies interact with gravity will change slightly. This obviously isn't quite the same thing as floating in space. Floating in space is not caused by a reduced level of gravity. It's caused by a thing what we call free fall, so a continuous falling of an object. All right, so firstly, like we said, the magnetic field on Earth provides a really important function. It helps us block out, really harmful solar flares. The other thing is the changes in gravity. Now, Mars is a much smaller planet than it is on Earth. We know that by mass and acceleration of gravity are directly proportional to each other. So because Mars has a lower mass than Earth, it also will have a lower acceleration due to gravity. As a matter of fact, as you can see from this diagram here, on Mars you experience about 62.5% less gravitational acceleration than you do on Earth. So this is the formula that's actually linked to how large the acceleration due to gravity is. This formula you don't really need to understand in year 10 science. However, it might be of interest to you if you are interested in doing year 11 and year 12 physics. So little g is the representation of acceleration due to gravity. So acceleration due to gravity. If you actually have a look, that represents the radius between the centers of the object. So imagine the Earth is here. This is the center point of Earth. This is the radius r. Big G is a constant, known as the gravitational constant. It's just a value of what we could say the amount of gravitational fields that can be exerted on mass objects. And then big M is the mass of the planet. Doesn't necessarily need to be mass of planet, it could be a mass of anything. But just for simplicity's sake, when we're talking about the acceleration on a planet, big M is the mass of different planets. So if I was to try and find the acceleration due to gravity on Earth, I can do a couple of substitutions here. So the mass of Earth is 5.972 times 10 to the power 24. The radius is about 6,371 times 10 to the power 3. If I substitute it into this equation here, okay, big G, here is some 6.67 10 to the minus 11. You times that by the mass of Earth, given by our formula here. And I know the answer is below, but just so in case some people were not sure how that value came together, I'll just write it again. And then the radius of the planet is given to you here. Now you can see there is a to the power of 2, so we make sure to square it. And we find that approximately the acceleration due to gravity is 9.81 meters per second squared. Remember, meters per second squared is the units for acceleration. So this is what we see here, okay? Now, depending on the gravitational acceleration you experience, you'll also feel a force. Now, this formula here is essentially Newton's second law of motion. Newton's second law of motion says that if you have a net force exerted on an object, they will accelerate in the same direction as your net force. Okay, so that we have here. So what we see on planet Earth, if we make the assumption that very close to the surface of the Earth, it's relatively flat, again, like we said, this is just an assumption. The acceleration due to gravity is 9.8 meters per second squared. That's the acceleration, which also means the force that is being pushed onto you is also in the same direction. So that's kind of how we work it out. We can also work out this force is actually called the weight force. So when we actually say, oh, how much do you weigh, we're not actually talking about the same thing. Usually we actually refer to mass. Okay, so your mass is how much, properties, chemicals, atoms that are inside of you. That's the measurement of mass. Weight force is actually how much your body experiences, how much force your body experiences due to the acceleration of gravity. Okay, so that's kind of how we work it out here. Your mass never changes. No matter where you go around the world, if you are 100 kilograms around the world, you are going to be 100 kilograms around the world. However, the force that you experience on your body will change depending on where you are in this universe. Okay, let's have a look here. Say if I'm an astronaut with a mass of 100 kilograms, my weight force is 980. Now the reason why it's 980, okay, it's simply 100 kilograms times 9.8. That's the acceleration due to gravity. So that's where we get this number from. If I was on the moon, I would have a mass of 100 kilograms. My weight force is 160. Okay, which means the acceleration due to gravity on the moon is a lot smaller than the acceleration due to gravity on Earth. And that has some consequences on our body structure as well. So what actually happens is if humans were to inhabit Mars, given that Mars has a much lower gravitational acceleration or weaker gravitational force as well, that actually has negative effects on our body long term. A weaker gravitational field means there's less force holding onto the minerals inside our bones. Now remember, the reason why Mars doesn't have an atmosphere is because it has a really weak gravitational field. So it's lost all of the necessary gases that make up the atmosphere. And so that's why it's always exposed to, solar radiation and all that. The same thing can happen inside our body when we lose minerals in our bones. As a matter of fact, we can actually do a little measurement of the weight the bones lose as a percentage per month. So per month, your spine in space, or at least under low gravitational forces, will experience a 0.8 to 0.9% loss. Your tibia, so your lower ankle area, as you can see those numbers there. And then your fibia, which is just your little joints near your hip area, about 2.27 outer, you can see that. So 90% of mass loss occurs in high density outer layer of the bone. So you're actually reducing the density of your bone. You can actually potentially cause yourself to have osteoporosis, which is actually why a lot of astronauts, when they're in space, they do a lot of weights training. Weights training is the best way to maintain bone density. So keep that in mind. Not only just in space, but for general well-being, weights are good in retaining bone density. Okay, so what we're going to do now is just do a couple of calculations on working out the acceleration of gravity on these different planets, and also the weight force of an individual based on where they're positioned in the planets. I'm only going to show you a couple of examples, and then the rest you can try yourself. So just remember the formula is G equals to big G times the mass of the planet, R squared. So, and I'll move it down here, big G is a constant value, so 6.67 times 10 to the power minus 11. It has a mass, Earth has a mass of 5.972 times 10 to the power 24. And then we get our value for the radius. Okay, and we find that the acceleration is around about 9.8 meters per second. Okay, if I want to find the weight force of a person with 100 kilograms on Earth, 100 times 9.8, remember, because it's mass times acceleration due to gravity, 980 newtons. Let's compare the acceleration due to gravity on Jupiter. So if I was to do the same thing using this formula here, 6.67 minus 11, the mass of Jupiter, and then squaring that by its radius. Okay, next I'll just need to put that into my calculator. Alright, so I got my value. Just make sure you also remember to square this. There's a common error that occurs, that even when I write it, I accidentally forget it sometimes, but just make sure you get that. So it's about 25.9 meters per second squared. If I was a 100 kilo astronaut in space, then I experience a gravitational force or weight force of 2,590 newtons. So you can see you would obviously not feel as comfortable as you are on Earth if you were in Jupiter, given how much larger your weight force is. So that's what we have there. All right, so if it's so dangerous, why do we go into space exploration to begin with? That's because going into space has brought us a lot of new technologies. If you could imagine going into space, you will not have a supply of fresh water. So the fact that we have water filtration technology, that's actually thanks to space travel. If we go into space, we tend to try and do some studies of nearby stars or just general surveying. And so we need cameras to take recordings of what we see. And so that's the invention of the charge couple device. You learned about this a couple of lessons ago. So that's the reason why we can learn about and take recordings of images. And then put an image of a plane here because the concept of planes is when you go into really high altitudes, it gets really cold. So water can simply begin to freeze. And so for planes, in order to not get frozen and cause quite a lot of danger when flying, they would have what we call anti-icing devices. And that is also invented because of space travel. As you imagine, going into space, it can be quite cold. And obviously, they just have a natural system of recycling different materials. So we could see recycling of oxygen, regeneration, water processing. So using recycled water as drinking water. That can improve humidity and temperature control and removing general waste products. Okay. And for those who really want to know, not all waste products can be reused or recycled in the International Space Station. So some of the times they might take it back to Earth to process it there. All right, so let's just look at some of the conditions on Mars. We said one of the most important things for life to exist is having water. Now, for Mars, we actually know that there are clues of the existence of water. As a matter of fact, the opal stone is actually one of Australia's national gemstones. They actually managed to find some opal stones on Mars. Now, the significance of that is in order for opal stones to form, this is the general chemical formula for it. You can see opal is created from the ligands of water molecules attached to it. So the fact that we have opal stones found on Mars would hint that there must have been water present at some point in time in order for this type of gemstones to be created or formed. As a matter of fact, we now have a better idea of what Mars kind of looked like back in the day. We actually believe, and the current understanding is, that Mars had a lot of liquid water. So it was split into two halves. One half was basically rocky land, and then the other half was basically a really, really large ocean. So that was the idea. Now, obviously, the question would be, why did the water disappear? If we have a look at it, could it be because it's too hot on Mars and all the water evaporated? Well, not quite, because Mars is actually within the Goldilocks zone, meaning that it's not too hot or too cold for life to survive, which also means that it's not hot enough to evaporate all the water away. If we actually look at the temperatures on Mars, we can actually see the fluctuations. So on Mars, this is in degrees Celsius, the maximum you'll ever experience on Mars is about, 30 degrees Celsius. The coldest you'll ever experience on Mars is about, minus 100, minus 120 degrees Celsius. You can see, obviously, it does have its own summer and winter months, but you can see it's probably not directly related to temperature on Mars, as it's not hot enough to boil away all the water. If we actually compare the pair, we can actually see on Mars, its maximum temperature doesn't get close to Earth's maximum temperature, but its lowest temperature is much lower than Earth's lowest temperature here. So what could be the reason for this big fluctuation on the two planets? And the reason for these fluctuations is essentially because the gravitational fields aren't strong enough to hold the water on Mars. Essentially, because Mars is a lot smaller than Earth, the water molecules essentially escaped out into outer space. right? Same thing applied with Mars's atmosphere. Over time, the atmosphere wasn't held strongly enough by Mars's gravitational field, and so they also begin to move outwards. And so that kind of gives us a nice explanation why there is no water, liquid water that is, on Mars anymore. Another thing we can actually tell from the fluctuations between the two planets is that Mars doesn't hold an atmosphere. Now, the reason why the atmosphere is important for Mars is because it holds greenhouse gases. Yes, greenhouse gases. So on Earth, our greenhouse gases actually help the planet maintain a certain range of temperatures. It will ensure that our planet, on average, isn't too hot or too cold on one side, whilst on Mars, because it doesn't have these greenhouse gases, or it's in really, really low quantity, you'll have sides that are facing the sun to experience, relatively speaking, a much higher temperature than the side that's not being exposed to the sun. So that's kind of the issues there. So, whether or not Mars is possible to be inhabited by people, there's a little bit more work to be done. As you can see here, there's a couple of factors that we need to look into about Mars. Anyhow, that concludes the lesson for today. I'll just end it with some little animations that I managed to find on moon exploration. If you found this series about Earth and space very interesting or useful, please give this video a like, and I'll see you next time.